Let's talk about Oblivious algebraic data types. Consider this mental game called Yale's Millionaires problem. Let's say Alice and Bob, two millionaires, want to decide who's richer without disclosing their actual wealth. In other words, they want to compute something together, in this case a boolean indicating who's richer, and they want to do so without revealing their private input, their wealth. This is an important problem in cryptography as it formally introduces secure multi-party computation, or in this talk, oblivious computation, that allows multiple parties to jointly compute something without leaking their sensitive data. This is useful in, for example, secure auction, voting, and privacy-preserving machine learning. While cryptographic solutions exist, directly using those techniques can be quite challenging, especially for non-experts. So with recent efforts in the PL community, we can write such applications in a high-level programming language. But what's missing is the support of rich recursive data structures like trees, whose shapes are also private in addition to their private payload, and we call these oblivious algebraic data types. Now, in this kind of applications, an attacker is one of the participants running the program, so they're very powerful. They can see the data in memory, which means we need to obscure the shape of the data in memory, and they can observe the whole execution, so we also need to protect private information from leaking through side channels. In this work, we introduce a core calculus for doing oblivious computation with algebraic data types whose shapes are also protected. It allows the users to choose what to disclose using types, and I will talk about why we need that later. And the type system ensures no private information is disclosed. Lastly, we also have a novel semantics to separate the program logic and the security concerns. More on that later. First, we need to acknowledge that it's not possible to have completely oblivious recursive data because the attackers can always see the data in memory. For example, if we represent a password as a list, even though all characters are encrypted, the attackers can still infer that this password is 3 characters long. In order to obfuscate the shapes, participants need to agree on a public view, which is essentially an upper bound on the shape of the data. For example, the public view for list could be the upper bound of the length. In this password example, let's say all participants agree that their passwords are not longer than 16, then all passwords will be padded to this bound to obfuscate the shape of the list. Our solution is to allow the users to choose what they want to disclose to make this obfuscation possible. To give you a teaser of what our solution looks like, consider this binary search tree example. A tree is defined in a standard way with bound integer payload, and the lookup function takes a search key and a tree and it returns if this key is in the tree. We can define a corresponding oblivious tree, treehead, as a dependent type with a type index being the public view. In this case, the public view is the upper bound of the tree depth. This type level function should compute to a type that stipulates the shape of the tree. We can also define it with a different public view, such as the upper bound of the spine. Now we can define an oblivious lookup function this way, and our type system ensures this program will be oblivious. However, in order to make the type system happy, programmers need to restructure the program to only depend on the public view. As a result, this program contains a lot of boilerplates and obscures the original program logic. What's worse is that if you use a different public view, now you have to write another lookup function and deal with different boilerplates, even though the high-level program logic is the same. But with our approach, you can simply lift the lookup function to the oblivious version by composing it with what we call section and retraction functions. The idea is instead of writing an oblivious lookup function directly, we can first decrypt the private input, and then run the public function on it, and finally encrypt the output back to the oblivious world. This way, we separate the program logic and what public views we decided to use. Of course, it seems like this approach is not secure, because as soon as we decrypt the private input, we essentially disclose all the private information. But the semantics and the type system of our approach will ensure the computation remains secure, so no private information is actually leaked. If you want to learn more about how that works, check out our POPL talk and the paper. We will talk about the core calculi we formalized, how we maintain the security guarantee, and other good stuff. Thank you.